Aha! Wait a second, Mr. Scapetus. There's a negative here. So this is negative mu k times g times t. True. So how can we have a negative time? Well, we can't. So let me remind you, the equation is a equals delta v over t, delta t. So that is final velocity minus the initial velocity over final time minus the initial time. Right? The initial time is 0, so that goes away. In this instance, our final velocity is 0 minus our initial velocity, which is not 0. Okay? So that means what we end up with is negative velocity over negative mu gt. Sorry if I skipped that. I felt bad. I wanted to clear that up. All right, moving on to II. We're looking for distance. Deriving an expression for distance, we have v, we have mu, we have g, we have a, we have t now. Boy, we have a lot to work with. We're looking for distance, so the equation that we can start with, the given equation, because we're deriving, so we will choose an equation that we already know. I like working with a no time equation. This looks like a lot of fun, but if I can get away from it, d, sorry, talking and writing at the same time. 2a delta d, right? Final velocity, we know that's 0, and we know that the initial velocity is whatever, so we're going to move the initial velocity to the left by subtracting initial velocity squared. Subtracting this whole term, so that negative is going to appear on the opposite side, equals 2ad, and we're solving for d, so it's going to be 2a from each side. And this is getting kind of lost, so I'm going to continue it up over here to the right in a different color. I'm going to rewrite, so give me just a second. Negative v naught squared over 2a equals d, because those went away, right? Acceleration. We can't leave it as just acceleration. We know what acceleration is here. Sorry for the bad editing. So plugging in, all I did was substitute the acceleration that we had previously found to be acceleration equals negative mu g, and then I just plug that in right there to get this equation. Negative v squared over negative 2 mu g. You can clean that up a little bit more. You can simplify it because those negatives are going to go away. So it becomes 2 mu g. The negatives go away, which gives us a forward displacement. We're moving forward and slowing down, like coming up to a stop sign. On to the next one. Explain how the expressions we did up here, this was t equals v over mu g, just for reference. Let's see, so we have v in the numerator for both of these equations, right? What did part A say? Part A said t and d is longer, brakes take longer to stop the car, right? So if we increase velocity, we're increasing time. If we're increasing velocity, we're increasing distance because they're in the numerator. So velocity is in numerator. So as v gets bigger, t and d do too. Okay, so more velocity, more displacement. More velocity, longer time. Your answer to part AII, so we know that more, what we said was something to the effect of more friction means less distance and time. Well, friction, denominator, so if we increase the denominator, what happens over here? This is going to get smaller. If we increase this, time will get smaller. So because mu is in the denominator, that says denominator. Bigger mu means a smaller time and distance. How would the values of T and D change if the car was replaced by a truck with a greater mass, but the same initial speed and the same type of tires on the roadway? Well, good question. Truck. Wait a second. It doesn't matter if it's a truck, a bus, a plane, whatever it is. There is no mass in the equations. That canceled out a long time ago. Mass got canceled out. Mass was canceled out. So in this specific situation only, mass doesn't matter. Mass was canceled out. Something to that effect, to where it doesn't affect time or distance. That's it. Thank you for hanging in with me. I know these past two videos were rough. This stuff is tricky. It's not impossible, but you definitely have to practice.